Lesson 9-1, Quadratic Graphs and Their Properties. Recall from Chapter 8 that a polynomial with a degree of 2, such as negative 16x squared plus 64, this polynomial has a degree of 2 because the highest degree is the exponent of 2. We called this a quadratic polynomial. This entire chapter, we are going to be working with these quadratic functions. So we can use this quadratic polynomial to define a quadratic function. Alright, so what is a quadratic function? It's a function that can be written in the form y equals ax squared plus bx plus c. And remember that in this form, it's in standard form. So standard form of a quadratic function is this. If it were in any other order, it would still be a quadratic function, it just wouldn't be in standard form. So 3x squared, even though you don't see a bx plus c, those values are just 0. So that is a quadratic function. X squared plus 9, x squared minus x minus 2. All quadratic functions, you're looking for that power of 2. Alright, now a quadratic function is nonlinear, meaning it does not produce a straight line. It produces this parabola. The parent function, meaning if we just had the original values, origin of 0, 0, and had a normal arc, would be y, or function of x, equals x squared. This is the parent function, or parent form of a quadratic. Now, like I said, I already mentioned the curve shape. This U-shaped curve is called a parabola. You can fold the parabola in half and it would have two equal sides. And those equal sides can be folded along the axis of symmetry. That axis of symmetry might be the y-axis. It usually is, but not always. This parabola could be moved over on our coordinate plane. And then, in a parabola, it can open up and it can open down. Always draw your arrows to signify which direction it's going. The vertex is the highest or lowest point on the axis of symmetry, meaning right in the middle. So the vertex can either be a minimum, because it's the lowest point, everything goes up, or it can be the maximum, highest point, everything goes down. Alright, so our first example, we're just identifying what the vertex is. So if you see a parabola, you want to find the coordinates and tell if it's a minimum or maximum. Well, here's the highest point. This must be a maximum, and it looks like I'm at 0, 1, 2, 3 is my ordered pair. Example B, I have a minimum, and my ordered pair is 1, negative 1. So I just found the middle or the vertex. Alright, you can use the fact that a parabola is symmetric to a graph, or is symmetric to graph it quickly. Meaning, so if we want to make a parabola graph, we're going to start by making a table. And if you just plug in a couple points on your XY table and you get the Y's, let's say that the X's gave us a couple points. And if we graphed that one side of the parabola, because a parabola is symmetrical, we could transfer those points across the axis of symmetry to quickly plot the other side. Let me show you what I mean. So here's the function 1/3 x squared. We're going to first make a table and then graph them. So here's our function, put it into our machine. We pick the inputs 0, 3, and 6. They put 0 in and they got out 0. They put 3 in and they got 3. They put 6 in and they got 12. So they went to graph those points 0, 0, 3, 3, 3, 3, and 6, 12. Now, because it's symmetrical, we can reflect the points from the table across this axis of symmetry, so over here, and now we can connect them and make our parabola. When you do this, you might be asked to state what the domain and the range are. Remember, the domain is all of our x values. In a parabola, the domain can be any of these x values. So we say all real numbers. Now our range, what are possible ranges? Well, let's see. 0 is our minimum, and everything goes up. So y has to be greater or equal to 0. So here's another example where if you get a parent function, a quadratic function, make your table, get your x values, plot them wherever they are, and then you can just reflect them over your axis of symmetry to make your parabola. Don't make it as poor as mine. And state the domain and range. All right. The coefficient of the x squared term in the quadratic function affects the width. Notice this one's pretty skinny, this one's very wide, and this one's in between. So this, when we have a function, the coefficient of the x squared term affects that width. So if we had two, mx squared and nx squared, if m is less than, the graph will be wider. So if we were comparing these three quadratic functions, -4, 1/4, and 1 are our coefficients. The smaller the coefficient, the wider. So our smallest would be, out of -4, 1/4, and 1, -4x squared would produce the skinniest parabola. 1/4 would be next, right here. And then 1 would be the order. So when we have coefficients like 1/4, 1, and -4, our widths will all be different of our parabolas. To know which one will give you the widest, you want to, for example, if we have two quadratic functions, y equals mx squared and y equals nx squared, if the absolute value of m is less than the absolute value of n, so ignore the negatives, so the smaller coefficient will have the widest graph. So in other words, looking here, -4x squared, well, that's a coefficient of 4, 1/4, just 1/4, and 1. The smallest coefficient between all of those is 1/4. So 1/4 x squared produces the widest parabola. Second would be our y equals x squared, right here. This is our second widest, and our narrowest is -4. So use those coefficients. Remember to take the absolute value of the coefficients and don't apply the negatives. The smallest coefficient will have the widest parabola. All right, and then if we take that y equals ax squared and then we add c onto the end, that's going to affect our graph up or down. So for example, y equals 2x squared, if we put in our domain values and put them into y equals 2x squared, we get this red parabola right here through the origin. Now if we compare it to the same graph but plus 3, notice it just moved 3 up on the y-intercept. So you can just use the table to be able to graph both of these. Just know that C affects the graph up or down. All right, our last example with our first lesson of Chapter 9 is the falling object model. So if you were to drop something, over time the speed increases. So the height that something is above the ground, as time progresses, it decreases faster and faster. So we're going to use this quadratic function to measure that distance. So height equals -16 times the time squared plus c. C is the object's initial height in feet. So let's say an acorn drops from a tree branch 20 feet above the ground. That's the initial height. That is our C value. The function h equals -16t squared plus 20 for the 20 feet above ground gives the height of the acorn in feet after t seconds. What is the graph of this quadratic function? And about what time does the acorn hit the ground? Well, they give you the function. We're going to plug in some domain values. Well, we always want to start at 0. After no time, the acorn should still be at 20 feet above ground. Then you want to pick some second intervals and get your points to plot. Once you have those, you can plot your quadratic function. Notice that as time goes by, the distance from the ground decreases very quickly. All right, so here's our graphed function. The acorn hits the ground when the height above ground is at 0. So when the height is right here, that would be hitting the ground. Looks like it happened a little after 1 second. That would be our answer. All right, so now is your turn to attempt the lesson check. Graph each of these parabolas and identify the vertex. Notice that in these two, the +2 and the -1 adjust the graph up and down. These three, the coefficients, affect the width of the parabola, and they all might have their own axis of symmetry. It'll be up to you to find it. Good luck.